This is the Mandelbrot set, one of the most beautiful and remarkable discoveries in the entire history of mathematics. Yet it was discovered as recently as 1980. The invention of the silicon chip in the 1970s created a revolution in computers and communication, and hence transformed our way of life. We are now seeing another revolution, which is going to change our view of the universe and give us a better understanding of its working. I'm Arthur C. Clarke. I write science fact and science fiction. You may know my movie 2001: A Space Odyssey. I've seen some remarkable developments and inventions in my lifetime, but one of the most extraordinary is the Mandelbrot set and fractal geometry. This film will explore the fractal universe, and on our voyage of discovery, we'll be helped by Professor Ian Stewart of the Mathematics Institute, University of Warwick, and author of over 100 published scientific works. Dr. Michael Barnsley, former professor of mathematics at Georgia Institute of Technology, who received a $2.5 million government grant in 1991 to develop fractal image compression systems. Professor Stephen Hawking, the mathematician and cosmologist, and author of the best-selling book, A Brief History of Time. And finally, Dr. Benoit Mandelbrot, whose unorthodox mathematics led to the discovery of the Mandelbrot set and fractal geometry.
I first saw the Mandelbrot set somewhere in the mid-80s. I remember it quite clearly. We were at a mathematical conference on something totally different, and everyone went along to this exhibition because it was mathematical pictures. And there were these amazing coloured pictures on the wall, and I'd really not seen anything like this before. It's not easy to describe the Mandelbrot set visually. It looks like a man, it looks like a cat, it looks like a cactus, it looks like a cockroach. It's got little bits and pieces that remind us of almost anything that you can see out in the real world, particularly living things. So it has a character that reminds us of a lot of things, and yet it itself is unique and new.
The Mandelbrot set is real, an absolute thing, no question whatsoever. Any mathematician or any computer scientist or student in a school can study it and find the same, describe the same thing. It's a common experience. And so such things that can be magnified forever and have infinite precision do exist, but they're not touchable.
It's a geometrical shape, an icon, if you wish, which somehow embodies as an example a very important aspect of how the world works. Somebody recently actually called this set the thumbprint of God.
Now we'll begin our serious exploration of the Mandelbrot set, a voyage which, in fact, could last forever and ever, much longer than the lifetime of the universe. I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, replicas, almost identical, yet perhaps subtly different, of the original set. And I can go on doing this. Here's a magnification of more than 3,000 times. So the original picture, about 6 inches across, is now half a mile across. And no matter how much we magnified it, a million times, a billion times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier of the M set is infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only or rather big, but this is really infinity. What is so remarkable, in fact, astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers.
I think the most important implication is that from very simple formulas, you can get very complicated results. It's fundamental from viewpoint of the very base of science, because what is science? We have all this mess around us, things are totally incomprehensible, and then eventually, more or less rapidly, more or less hard to achieve, we find simple laws, simple formulas. In a way, a very simple formula, Newton's law, which is just also a few symbols, can, by hard work, explain the motion of planets around the sun and many, many other things to the 15th decimal. It's marvelous. A very simple formula explains all these very complicated things.
There's an interesting parallel with the equation that almost everybody is familiar with, the only equation almost everybody is familiar with, E equals mc squared, Albert Einstein's equation that says matter and energy are equivalent to each other. That was a very simple equation with very far-reaching consequences. And the equation for the Mandelbrot set is equally simple. Z equals z squared plus c.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities, mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane, defining the location of a spot. Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of a two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves. This process of going round and round a loop is called iteration. It's rather like a dog chasing its own tail. The output of one operation becomes the input of the other, and so on and on and on. When the Mandelbrot equation is given a number representing a point, and that number is iterated through the equation, one of two things happen. Either the number gets bigger and bigger and shoots off to infinity, or it shrinks to zero. Depending on which happens, the computer then knows where to draw a boundary line. So what we get from this basic iteration is a kind of map, dividing this world into two distinct territories. Outside of it are all the numbers that have the freedom of infinity. Inside it, numbers that are prisoners, trapped and doomed to ultimate extinction.
One of the most striking facets of the Mandelbrot set is the internal consistency of the object. It all hangs together. And if you look at the boundary and zoom in, if you look in just the right place, what you see is baby Mandelbrot sets, perfect in every detail. They're just slightly bent compared to the real set. You can't even see that, but if you look closely, they are. And they're decorated by slightly different external features. And then by the same token, if you zoom into the boundary of those, you see baby Mandelbrot sets, the second generation. And inside those, the third generation. It goes on forever. And so you're seeing islands of order in a sea of chaos.
I'm sure it's occurred to you that the Mandelbrot set looks like some kind of strange insect. It certainly has an organic feeling about it. It's got warts all over it, and it's also quite hairy. If we go out along one of those hairs, we find something rather interesting. Now look what's happening. At the tip of each hair it splits into two others, and so on. Each is splitting, going on indefinitely. This splitting up, this bifurcation, going off into apparently random directions quite abruptly, is typical of a class of mathematical entities called fractals. The Mandelbrot set is the most famous fractal.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realised he was working in. And so he coined the term fractal because it conveys this feeling of fragmented, broken, fractional, irregular.
One of the revolutions in thought that's resulted from this discovery is the realization that nature deals not in smooth, continuous objects, as we always imagined, but more often in fractals. And I'd like to show you how she does this. Now I'm going to generate a fractal before your very eyes. What you see here is what's called the seed, and it's an appropriate word in this case. Those two lines represent the first generation of the formation of a geometrical figure. And the computer has been told to continue growing these lines, but changing the direction every so often and at different distances. Now that's a very simple set of instructions, but look what happens after they've been carried out for, say, 10 generations. The tree I showed here, and it does look very much like a tree in nature, is symmetrical because the two branches at the beginning were the same length, off in the same direction. But if we change the length of one branch and change the direction, look what happens. In a way, this is a more realistic tree than the first one, because in nature you seldom have perfect symmetry.
The discovery of fractal geometry changes completely the kind of patterns we can look for in nature. And that is a really fundamental change to the sort of things mathematicians and scientists can do. And that's got to have a big effect.
Fractal geometry is already being applied throughout the physical sciences as a way of describing data in a new way. And the dream is that a fractal geometer can describe a cloud as simply as an architect can describe a house.
I'm looking at Saturn, one of the most beautiful objects in the sky. In fact, we've discovered quite recently that the beautiful rings of Saturn, which have intrigued astronomers for centuries, do illustrate some of the phenomena we've been discussing in the Mandelbrot set. As you go closer and closer to Saturn, you see more and more detail which no one had ever dreamed of before the space age opened and we were able to get close-ups of Saturn and its rings. It's not surprising that when we have so many examples of fractals and related phenomena here on this planet, there are even more in the heavens.
To me, just looking up at the Milky Way is staring at a fractal. It's got an extraordinary dotty character, and yet if you take a magnifying glass to it, that is a telescope, and you look at it ever closer, you find that there are hundreds and thousands more little dots where you thought there was almost none. So you get an immediate example of a structure that seems to go in and in and in with more and more detail.
I had the great privilege of having a discussion with the famous cosmologist Stephen Hawking when I passed through London recently. And I said to Dr. Hawking, the Mandelbrot set is infinite in detail. You can explore it forever and ever, zoom into it. The real universe, however, does seem to have limits. As you go down into the micro world, you get, of course, molecules, atoms, neutrons, and perhaps subatomic particles, quarks. But does the real universe go on forever? Is there a limit, a basement, unlike the Mandelbrot set?
In the case of the universe, there seems to be a limiting scale. It is called the Planck length, and it's about 1,000,000 billion times smaller than an inch. This means that there is a limit to how complex the universe can be. It also means that the universe could be described by a theory that is fairly simple, at least on scales of the Planck length. I just hope that we are smart enough to find it.
He thinks that there is a limit in the real universe. There's a small size below which nothing exists, called the Planck length, which is about 1,000,000,000,000,000,000 millionth of a centimeter, unimaginably small. But that is the fundamental unit of size, the sort of grittiness of the universe, nothing smaller than that. So perhaps the real universe does end there in smallness, but we're not sure. It may indeed go on forever. I'm often asked, well, these pictures are all very pretty, but what's their practical value? And I'm tempted to answer in the famous words of Faraday, who once said, when someone asked him what use were these experiments playing with wires and magnets, what use is a newborn baby? Faraday is also supposed to have told the Prime Minister, one day, Mr. Prime Minister, you'll be able to tax it. Fractal geometry also has surprising applications in medicine. This is the blood circulatory system of the human body, and yet you'll recognize it. It is a kind of fractal. Now we can understand what is really happening when our blood circulates. Here is the most important fractal of all in the human body, a small portion of the incredibly complex wiring circuit of the brain. We may never understand how our brains work, but if we do, I suspect they'll depend on some application of fractal geometry. Here's another strange resonance. This series of paintings was made in 1928 by a patient of Carl Gustav Jung, the co-founder of modern psychology. Jung would have been surprised and delighted to know that the computer revolution, whose beginning he just lived to see, would give new impetus to his theory of the collective unconscious. The idea that there's a well of consciousness compounded of primordial universal images that we all share, the substructure or background of awareness. The mind clearly finds resonances in the M set, but there are other wider implications too. This mathematics offers new insights into the way the universe works, how much in life is determined, and how much is due to chance.
When Isaac Newton came up with laws of motion and laws of gravity, the picture that emerged was of a clockwork universe. It was of a machine that ticked on a predetermined course. All we needed to know was where it was now and what it was doing now, and then you could predict the future forever. And there are two challenges to this. One is quantum mechanics, which says, in fact, there is irreducible chance built into the very fabric of the universe. And you can't actually say exactly what it's doing now. You can't say exactly what it's doing, ever. But the other is things that come out of the Mandelbrot set and related parts of mathematics, which is that even in a Newtonian world, in practice, you may not be able to predict the future. It can be deterministic in principle, but not in practice.
This is how God created a system which gave us free will. It's the most brilliant maneuver in the universe, to create something in which everything is free. How could you do that?
Albert Einstein refused to accept the idea of a dice-playing deity. He wrote a letter to Max Born in which he said, "You believe in a God who plays dice, and I in complete law and order." So he obviously felt that chance and deterministic laws were not compatible, and he preferred the deterministic laws. Now, what the Mandelbrot set and chaos and related things have done for us is to show that you can have both at the same time. So it's not whether God plays dice that matters, it's how God plays dice.